Thank you for coming. I'll just leave this up for another minute in case anybody wants to download the slides. There's only one directory in there, so it's a new repo. So I'm not actually expecting anyone to run the examples, but if you want to follow along, it's useful. So my name's Ryan. I work in the engineering group at Yhat by day. It's pronounced Yhat, not Yhat, not Yhat. We've heard them all. We do data science infrastructure, collaboration tools, and things like that. We have a really cool blog and some cool products, so check us out if you don't know us. It's cool stuff. By night, I'm a PhD student in operations research, eternally working on my dissertation, if that sort of fills you in on what the topic is going to be like a little bit in here. This is going to be a little different from some of the talks at PyData in that there's actually not going to be a whole lot of data in here. There will be some data, but the purpose of this model is partly to show how complex decisions can be made using Python and open source tools like that. You don't necessarily need to understand all of the modeling components that go into this. A few salient points are that, one, we don't need big data to have intractability. We can make problems very hard with very small amounts of data. In fact, we're practically surrounded by intractability almost all the time. But second, that intractability is not a death sentence. We regularly solve hard models and get useful answers out of them, sometimes even optimal solutions to problems. And that third, one of the things that makes things either very easy or very hard for modelers is the interplay of data and structure. And so the problem that we're going to look at today, while it may not be particularly interesting to you, I think it's very interesting structurally because it gives us sort of techniques or shows techniques on approaching a problem that is otherwise very hard. So we'll start by setting the scene a little bit. Who of you knows or feels like you have a good idea of what DevOps is? Raise your hands. Who knows what it stands for? I actually don't know what it stands for. Is that what it is? OK. All right. So I think of Scotty as sort of the archetypal DevOps engineer. He's constantly putting out fires. Somebody forgot to test their code or something and just stuck it into production, and then the machine goes down. Or oh gosh, someone unplugs a network cable and the box just catches on fire. Or somebody just keeps trying to ram their random forest model into memory even though they know it won't fit. They call on Scotty to fix that for them. But one of the more important things is that Scotty maintains all of the environments and the hardware that our IT infrastructure depends on. So that is one of the fundamental roles of DevOps, is creation of environments for building your software, for testing your software, for distributing your software, and for running it in production. We could not do much of anything that we do without DevOps. And especially when it comes to cloud computing, DevOps is playing an even more important role. There's even a Venn diagram about it, and we all know how much we love Venn diagrams here. This is the sign of a true profession. I mean, like the data science Venn diagram, you can sort of overlay it, and here we have the DevOps diagram. But it is pretty much the culmination of software engineering, QA, and technology operations. That is a pretty good description, I think, of what DevOps does. So let's consider a typical day in the life of a DevOps engineer. You're working on a Java project at yet another enterprise Java application running on enterprise software company. We all know that Java makes lots of money, so that's a cool thing. But then, I don't know, shell shock comes out, or some other utility needs to be upgraded. You can't just take your application and run it on new systems without testing it. So you now need two environments. The first environment is the existing production environment, where you install your Java application, Java compiler and runtime environment. You download all the dependencies and libraries that it needs to run on, and then you set up your database. The second environment is all those same things. So we're going to call these commands A, B, and C with an additional command D, which is to upgrade that underlying system utility, whatever it is. So now I have two environments that I need. One is my testing environment. One is my production environment. If my testing environment passes tests, I'm going to switch it over to production, and then we'll be good. Oh, I forgot. I also need to integrate with Postgres and MySQL and Mongo. And my software runs on Red Hat, and it runs on CentOS, and it runs on Ubuntu. So as I add these things, I have more structure and more environments that I need to test in. And the problem with that is that it's not additive, it's multiplicative, right? If I'm really thorough, I need to test in every single combination of these things. And so my DevOps engineer is going to be working all weekend, probably looking for a new job. If you've been in IT long enough, or you work for the sort of organization that has a room like this, you remember that before cloud computing, we all had these rooms that were overly air-conditioned, where we kept all of our hardware. And it's really, it's still like this, right? At some fundamental level, when you go onto the cloud and you ask for a computer, it's still just somebody else's computer sitting in a server rack like this, right? Like, the magic of cloud computing is that it's available to you all the time, but still somebody has to go into a room, or something has to install an operating system, or at least a hypervisor on a machine, maintain it, make sure that it doesn't fail, have it networked the right way, so on and so forth. A lot of the time, or a lot of the way that people would create fresh environments for testing and development back in the day, where they would go and they would take their installation media, and let's say you were going to upgrade Oracle, you'd grab your SunOS CD and you'd grab your Oracle CD, and then you put on your winter coat, and then you would walk into the server room, and 3 hours later you would emerge with a new, freshly built piece of hardware. And this was really inconvenient, right? Because it took a long time, and you keep doing that, and then you spin your disk to death, and you have to get another one. So what people would do instead was they would just uninstall things and then reinstall it and hope for the best. But that's not really good either, because software leaves relics behind. So you're sort of in this catch-22 of, it's either going to take me a really long time and I can be thorough, or it's going to be quick and I can be sort of not thorough and hope for the best. This is what we do now. So this is, of course, the Docker whale just running in a cloud. And that's kind of how we think of DevOps these days, right? We just spin up a container, and it's like, oh, well, there it is. And it's in a way, it's kind of true. Every time we spin up a new container with an image, it's like it's just, fresh born and pure as the driven snow. It's like nobody's tampered with it, right? And that's kind of awesome. So our next topic is, what's a container? I've been getting these two questions a lot this week. First, what's Docker? And second, should I be using it? So I'll attempt to answer that the best I can. Docker is a container architecture. What is a container architecture? It's a lightweight virtualization platform. There's lots of different kinds of virtualization. If you haven't used Docker, you've probably used something like VirtualBox, and that's a sort of a software virtualization layer. And when I use something like VirtualBox and I install, say, Ubuntu on VirtualBox, what that is doing, in a sense, is an actual install of the operating system onto virtual hardware. So when I boot up and I use Ubuntu inside of VirtualBox, it is as though I am sitting on the installation of the medium or the OS on hardware, and there's a translation layer, right? It has its own kernel, it has its own device drivers, and there's performance degradation to that. Docker is a little different, and other containers like LXC, container architectures like LXC, are a little different in that they do not do that. They do not have their own kernel. They do not have their own device drivers. They do not really wrap much. They depend on these functions within the Linux kernel that allow them to live in their own namespaces and have their own resources, but not be fully virtualized. So when you're running a Docker container, it's as though the Docker container thinks that it's its own operating system, but it's really not. And we'll see that in a minute when we do a demo. So I am going to create a Docker container. All right. Should I make that a little larger? How's that? All right. So the IT tells it to go into interactive mode. TTT gives me a TTY so that I can actually type things to it. And I'm going to save my SID. A SID is a container ID. So every time you start a container, you get a new ID. And I'm going to run the Ubuntu trusty image. And inside that container, I'm going to run bash. So when I run this, it tells me that Docker's not running. Sorry?
You said SID's a container ID.
Yeah.
Like it was a file and you moved it.
So let me just start Docker real quick. Okay. All right, so the SID file equals, it says when you spin up the container, find its ID and save it to this file. And I'm just doing that for convenience so that I can show you some other stuff in a minute. So any questions about that? I have the Ubuntu trusty image downloaded already. Otherwise, it would just go and download it, and we'd be waiting here for a good 15 minutes. All right, so I do this, and I'm now sitting at a bash console, and you can see that I am root. And this weird looking string here, that's part of my container ID. It's just SHA, right? So if I type who am I, I'm root. If I type PUSAUX, there's really only these 2 processes running, so it's shielded from the rest of the processes in my operating system. If I type cat lsb release, etc lsb release, it thinks it's Ubuntu. And this is kind of interesting because I'm running Fedora, right? But I can apt-get things. So I'm running a Fedora kernel with Fedora device drivers, but I have a container that thinks it's Ubuntu. And this is really useful because I can build code that targets Ubuntu C libraries that ship with Ubuntu 14 on my Fedora box, which won't work otherwise. Like if I just build them on Fedora and stick them on Ubuntu, they'll fail. All right. So yeah.
This is running on the same hardware as your Fedora machine.
Exactly.
And that's your computer right there?
It is, yep, exactly.
So you're not talking to a cloud at all?
No. There is a Docker daemon that it is talking to, but it's just talking over a local Unix socket connection.
Okay. So you just booted up Ubuntu on your Fedora machine.
Essentially.
Downloaded it previously.
Yeah, I downloaded the image. And we'll see that in a minute. So I'm just going to, what I'm going to do is I'm going to mess with this, and I'm going to commit those changes to an image, and then we'll see what happens from there. So I'm just going to do something crazy. I'm going to remove my password file, because sometimes you do that, right? And yeah, I mean, I'm going to create this thing. It'll be just a nice way to. All right. And so now, okay, you see from the root at FCE, that's my container. I'm going to go back to my host. This is my host, right at localhost. All right, so I've got this one guy running, ecstatic Feynman. He seems excited. And what I'm going to do here is I'm going to look at the differences in that container, how it has changed its environment. And this is where that container ID file becomes useful. So I changed the etc directory, I deleted the etc password, and I added the ingredients file. This is like a git diff, right?
With respect to your local machine.
Exactly. And now I'm not typing using git. I'm using Docker. Docker commit. And I'm going to call this Ryan PyData. So that nasty thing that it just gave me is the SHA for my image. And I can go exit from this guy. And I can run I have no name. Why is that? I deleted my password file. Oops. Right, so all the changes that I made have now been committed to this new image. That is called a layer. So if I go here to my host machine and I do Docker history, Ryan PyData, it will show me that I last changed it 38 seconds ago. The changes are 14 bytes. This is kind of nasty. Okay, there we go. 14 bytes large. That was the contents of that diff. And that was based on this other previous layer, which is really just Ubuntu Trusty. So it's a series of layers. Each layer is essentially a diff. And under the covers, what it's doing is it's using what's a union file system that sort of backtracks through those diffs when I look for files. All right. Any questions about Docker? Yes? I have a Fedora Linux machine here. Yeah, running Docker. You can run Docker on a Mac or Windows, but you're still really running a Linux kernel, like somewhere, because it depends on things on there. So usually what that is like there's now 2 levels of virtualization, and it works okay. But I take a small amount of triumph in the fact that I've switched all of our devs to Unix or Linux. All right. So back to here. Okay. So the second question was, should I be using Docker? Well, I don't know. I can tell you that at Yhat we use a lot of Docker. We build our software, we build our binary distributions inside of it. We use it for testing, we use it for development because it's much easier to spin up a MySQL database inside of Docker and give it a fresh schema than it is to worry about migrating things. And if we change our schema 10 times a day, we can just spin up new Docker containers with the fresh schema and it's very fast. We also use it for productionizing predictive models. So we use it in both sort of development, QA, and we also use it in production. So our ScienceOps product, when you deploy a model to it, you specify the exact environment that you want it to have, i.e. the version of pandas, the version of CVXOpt, whatever. It wraps those up into an image, which can live in perpetuity. So even if those modules go away off of PyPy or Conda destroys them or whatever crazy thing happens in the world, you can back up that image and you will always have it. You can always run your model in that image. And we also use it for our collaboration tool, Science Cluster. See, how much time do I have? Probably not enough time to show that. I might show that at the end if I have enough time. But it allows us to give management of Linux environments to users as though they were root on a system when they're really not. They can install packages, they can install Python modules, they can do all kinds of things, they can run Jupyter notebooks inside of containers, and then they can share those environments with other people if they want. So it's a very convenient way of just packaging up what looks like an operating system and shipping it around. So there's sort of 2 points here. One is that containers are about isolation. I can change an image, I can do whatever I want to it, and it won't affect my host operating system unless I do something weird. And it won't affect the other images inside of Docker. But they're also about sharing, and that's what we're coming to next. Specifically what we're interested in, do you remember how we have all these layers here with their SHAs? We're interested in how we can utilize that union file system mechanics to make our DevOps time shorter in constructing our environments. Because if we can use that effectively, then we can shorten the amount of time that it takes to construct all these environments that we need, which is good. All right, so let's talk about how Docker does cache mechanics. This is really what defines our problem. This is our structure. So let's say I'm kind of an odd bird, and I really like revision control systems that are out of date. I spend a lot of time on SourceForge. Everyone needs a hobby. All right, so I found last week, I found somebody who was actually using Bazaar, and then I had an old CVS repository, and I was like, oh, I just want to mech around in this. So I don't want to install it on my host operating system because I don't want to get it dirty. So I create this Docker file, and this is a standard, this is how you do this. This is how you create an image in Docker usually. So I'm going to start with Ubuntu Trusty, and I'm going to just apt-get install BZR and CVS onto it. Okay, great. This is the command that I used to build it. So you can see here, I'm giving it the name of that Docker file that I just created, and I'm going to tag it with RCS1, Revision Control System Image 1. All right, great. So when this build command runs, the first thing it does is it says, okay, start with Ubuntu Trusty as your base. It says, I've already got that. Great. The next thing it does is apt-get installs BZR. Well, it doesn't have that. So this time it actually goes through the whole process of apt-getting. And this will take a few minutes. And then it does the same thing for CVS, right? So there's actually 2 layers that I've created here. And at the end of it, it tags the last layer as the image, RCS1. So now I can go and I can Docker run RCS1 -c, which CVS and which BZR, and you can see that I have both of them. I could enter a container and I could run CVS if I wanted. Any questions about this so far? Okay. All right, but now I find like an old RCS repository, right? Has anybody actually used RCS? Yeah, you too? Okay, cool. Was it actually the first revision control system? I mean, it stands for Revision Control System. Okay. It was like CVS without networking, essentially, right? Like, first there was RCS, then there was CVS with networking, and then there were atomic check-ins on Subversion, and then there was distribution on Mercurial, and this other thing that rhymes with what I say when I try to use it sprung up, and everybody seems to be using that now. But anyway, so I find like an RCS repository I want to try. So I'm going to add that to my image. All right. So I'm going to create a new image called RCS2. And the first 3 commands of my Docker file are the same. But I'm now adding these 4 commands that allow me to add RCS because I find like a PPA for it. All right, so what should happen? So I build this guy. And the first 3 commands, it says, I've already done this before. I'm not going to do it again. Docker cache. Now it gets to the new steps, and it says, I haven't done these things before. I'm going to run these commands. So these layers are then added to the Docker cache as it does them. And at the end of this, I have a new image, which I can run CVS, RCS, and BZR in. OK, so now if I rebuild the same image, we'll see what happens is every single step, it's using the Docker cache. I don't have to do any of it again, right? So this sort of gets to the point, like if I can structure these, if I have a bunch of these files and I structure them correctly, then I can share a lot of this computing time. Yes?
Sorry, this might be a very basic Docker question. What's the benefit of this? Maybe I missed it. What's the benefit of this approach versus sort of doing all these things once, like you did in sort of interactive mode, and then just chipping that?
Space and computing time. That's really it. It saves on those things. If you had to have a flat image for every Docker image, it would be too much disk space. There wouldn't be enough in the world. All right, so this is great because like I can just run this over and over again, and it will just never take up any time. But what happens if I reorder it? Because I'm sort of a neat freak, right? So I want my add apt repository to be before my apt gets. Well, that actually breaks the cache. It sees that it has Ubuntu, but it hasn't run these commands in this order. So then it has to do all the same thing over again. Okay. So let's go back to our initial example where we had two images, one with ABC, the other one was ABCD. Let's check on the time. This is the optimal way to build these images, right? If the nodes on this graph are the commands being run, and the arcs where it says T of A and T of B, those are the time it takes, then we will incur every command exactly once. But if I structure it incorrectly, then I will incur ABC twice and D once, which is the worst case. Important thing to note, once two paths have diverged, never can they come together again. So if I think that I can do this for generating ABD and ACD, I can't. What will really happen is this, and I will incur the cost of D twice. The better way to do this would be to do AD, then split on B and C. And this would be my optimal solution. All right, let's do a problem formulation. So okay, what are we trying to do? We are trying to take a set of Docker files, a set of commands, and structure them so that we can make the most of the Docker cache, so that we can use the least amount of computing time to create these images. So there's sort of a corollary between maximizing use of the cache and minimizing the amount of compute time. They're really the same thing. So just some notational stuff. Let's start with C. We have a set of commands that we might run. Each one of these commands has a positive time. That seems reasonable. We know a priori the set of images that we need to create. Sure. Also, we probably know the times for these commands, right? We can at least estimate them. I mean, if we're doing this every day or every week or every month or something, we could time them. We can look at the logs. We know how long it takes to build a kernel, whatever. And C sub I is the images required for any I in the image set. We're also going to define this set P, which is we'll make a little more sense in a bit. It's the set of images that a command applies to and the commands that you run such that you share the cache. And we're going to seed that with single image command pairs. So for this example, we have images 1 and 2. Image 1 runs commands A, B, and C, and image 2 runs A, B, C, and D. So we're just going to seed P with 1A, 1B, 1C. So what is going to happen here? We're going to run each command for each image, and we're going to get our worst case out, right? So that's what we're going to expect to see. So for each one of these things in P, we define a binary decision variable. So it's either on or off. And if it's on, then we run that command for that image. So this is what that model looks like. We're trying to minimize the time it takes to do it such that we do everything. The output is just ridiculous. We run every command for every image. The total time that it takes is 2 times the first 3 times plus T of D. And that's what it looks like graphically. So we're starting at the worst case here. How can we improve it? Well, we know that we share A, B, and C through both the images, so why don't we create a variable for that? So we'll create a variable that says, if it's 1, then run commands A, B, and C for both images. If it's 0, then don't. So then that changes our constraints, because we can only run each command for each image once. So now x1 sub A plus x sub 1 to ABC equals 1, so on and so forth. We have to make a choice between these things, right? So this is our new model. And you can see this is pretty much the addition to it is this plus ta, t sub b, t sub c times that new variable, and the constraints have changed. So what is the optimal solution to this one? Well, obviously, it's that we share as much as possible. So we share the commands a, b, and c for both images 1 and 2. And for the one command that image 2 has that image 1 doesn't, we run that. So x sub 2d is 1. And this is our optimal time for creating these images. And that's what it looks like graphically. So that's correct. But it's not, unfortunately, always so simple. Let's consider this other case. We have 4 images to create, 3, 4, 5, and 6. And there's a lot more ways that these can overlap. For instance, I could overlap images 3, 4, and 6 with B. I could do 3, 4, and 5 with C. I could do 4 and 6 with D, and so on and so forth, right? So I have sort of initial stage decisions to make and then decisions that depend on those decisions, right? So if I share C, command C between 3, 4, and 5, then I might be able to share command B between 3 and 4, or I might be able to share command C between 3 and 5. But only if I do that, because they have to be on the same path. So this is one possible optimal schedule for that. So here you see I would share C for the first 3 images and then share B for the first 2. And then everything else would be run for every image. Or if T of A is large enough, it could be this, where I actually share C between the first 3 images and A between the first and the third. Or maybe D becomes very large, right, in terms of its time. And then all of a sudden I'm sharing D between images 4 and 6. So there's a lot of different ways that go depending on the data. But let's say we decide to share C between the first 3 images. Now what I do is I create new variables that say, let's assume that I've shared C. So I've made this decision, C for the first 3. I could now share B, or I could share A. So those are those 2 variables that I've created there. And that's why they've got the super long subscripts. But these variables are dependent on that first decision, therefore they have to be less than or equal to it. They can only become 1 if that other variable is 1. And I just add these to my model, and it will do the right thing. So if I know all the right sets to generate, then my model is pretty easy to formulate. And really, it's just an issue of figuring out what those sets are and restricting it to make sure that you do the correct thing. So here's kind of what it looks like mathematically. It's pretty simple looking, if all things considered. And if you've ever studied any combinatorial optimization literature, this will look very familiar. But we'll get into a little more into the structure later. So all we really need to do is know PNR. That's it, right? Simple. All right, so then the question becomes, how do we generate these sets that allow overlap or that allow sharing of commands? So this is sort of the cheater's answer, because it's the answer that I can cover in the time that we have. The first thing you do is you generate cliques, right? So what is a clique? Essentially what we're trying to do is find sets that can maximize our sharing at any level, right? So maximum clique, or maximal clique is, let's start with a clique. A clique is it's a graph where every pair of nodes are connected, right? So here we see that 5, 2, and 1 are a clique. 5 and 1 are also a clique, but they're not maximal because they're a subclique of 5, 2, and 1. So to generate all the cliques for this guy, I take all the images on the left and all the commands on the right, and I connect them as they are already. And then I connect all my images and I connect all my commands. And then I just set this up in Python. So here we define our commands, the commands that it takes for the images. We're just going to create some times. And we use network X. And so this outputs the following cliques. These are the top level ones. And then if I wanted to go create the dependency cliques, I would just run this again on things that are left over. So let's say we've made that decision to use C, to share C. This is the graph that is left over from that. I do the same procedure, and I just do this again and again. And so now I have these variables which I just add to the original model. And as long as I've got my dependency constraints correct, it will solve. So the problem here is that clique detection is NP complete. So we tend to kind of avoid things like that, right? Not necessarily. Things are maybe very intractable in theory, but real-world data doesn't necessarily look like that. We tend to, in theory, worry about pathological cases, and actually there are very good algorithms for clique detection and near clique detection that run pretty quickly. So I can deal with this. There are other techniques you can use where you don't really need to generate all of the data. You could generate enough of the cliques that your answer is going to be good enough, and you'll improve pretty well. Which just brings us to this section. So once we have our cliques, we need to actually put this all into a model. We've got a bunch of variables. We've got something that looks like a set partitioning problem. How do we solve that? So we're going to use the open source library Pulp, which is an algebraic modeling system. If you haven't used it, it's really nice. Makes it so you don't really have to think about like the matrix structure of a linear optimization problem, which is fun. So what does a set partitioning problem look like in Pulp? Basically looks like this. You can either minimize or maximize a set partitioning problem. And again, set partitioning is NP complete, but we're just not going to worry about that. It's one of those problems that's not solved in any way, but we're wicked good at solving set partitioning problems. We've got heuristics that are excellent. We've got pseudo-polynomial dynamic programming algorithms for doing it. So we're gonna use one NP hard problem to generate the data for another NP hard problem, and we're just gonna call it good. So this is what that looks like. I'm going to solve the problem with the 4 commands or the 4 images, each with 3 commands. So here we just create the binary variables that allow each image to incur the cost of all of its commands. And I know the cliques because I ran the code that we had. So these are a bunch of binary variables that allow us to do the sharing. This is sort of the top level of that. And then this is the secondary level of that. So these are the ones that are dependent cliques. These are the actual dependency constraints. And then this restricts the intersections between them. You can write code to make this cleaner, but I think it's just a lot more obvious if you just spell it out for demonstration's sakes. All right, so we add constraints saying that each command or each image runs each command exactly once. And our objective here is to minimize the compute time. So that's the time for each clique. We set our objective, run it, and this is the output. So the time takes 67 whatever units of time, minutes, seconds, I don't know. And this is our schedule. So this is not immediately usable. We have to construct a schedule out of this. But it tells us to share A and C for images 3 and 5, and B and D for images 4 and 6. And then everything else just incur the cost for the image. So we construct that. So we share A, B, C, and D, and we just add the other stuff at the end. All right, so let's do an actual computational example. This is generated data, but yeah. At some point, I'm going to go in Docker Hub and maybe restructure some of their images, but for now. So here we have a set of 15 images. The commands are just numbers, and these are randomly selected. And each one has just a random amount of time. These could be seconds or minutes or hours. And we run it through our model, and this is the optimal construction schedule. So if we just wrote our Docker files like this, we would make maximum use of the cache. And our total time would be 9,414. All right, so what does that mean, right? I need something to compare it to. So let's come up with a heuristic. So this is the most common heuristic. It's essentially greedy. At every stage, let's just select the most common image and move from there. Or sorry, most common command and move from there. Is really all it is. So I run that, and now I have another schedule, and we can see it's about 10% different. But it does the same thing, but we've just saved that amount of time by optimizing fully. Now this is also a lot better than you would do if you just tried to run them. But it's your gap between heuristic and optimal solution. So that's about it. I know I went pretty quickly over the optimization stuff. I didn't really want to talk too much about that. I think there's actually another talk about that later today on the schedule. But are there any questions? Yes.
So theoretically, you could also get a lot of performance by reordering your Docker files.
Yeah.
Like
Yeah.
internally. But that seems a lot harder.
Yes.
Because like you have to detect
Yes.
which commands are dependent on other commands inside of the Docker file.
Right. You mean an existing one?
Yeah.
Yeah. You could do that. I would think I would approach that in the cost of restructuring them approach as well. Like how if I change this existing Docker image that I have and I move this command forward, I have to run everything after it. And what is the cost of doing that? But yeah.
Those could be shared amongst other Docker. Like that just seems like
Yes.
the problem just explodes.
It does, very much so. Yeah. Any others? All right. Thank you.